these organisms is they have something called a hyoid bone that presses gently on the outflow of their jugular, which pulls the blood a little bit, creating a casing around their brain so that there's not as much sloshing. So it's just a little more rigid. And that does the same thing. Bears, of course, coming out of hibernation about a month ago, their bones, even though they didn't move much in hibernation, come out stronger. When we go up to space, we experience extreme osteoporosis, right? Because we're not moving around as much and we're not having that stress, and so we have osteoporosis. That's why strength exercising is good for your bone health. Bears have a way of actually strengthening their bones. Their bones come out of hibernation stronger than they went in. They also don't urinate or defecate. If you and I did that, our glucose levels would rise. We would be extremely diabetic. They don't get diabetes. So we're trying to understand how that works so that we can so doctors can create treatment for this. So I hope you see a bear. You may not hope so, but when you do, thank them. You're going to see lots of butterflies because this is wildflower season. This is kind of exciting. There is a new cancer cell detector. It is not a fancy piece of equipment. It's $20. And it's based on the butterfly's eyes and their ability to see certain wavelengths of light. And so when you go to get your next cancer treatment and your cells fluoresce, this little sensor can see that. There are sensors right now that look for that, but it can see it 1,000 times better, deeper. So you may owe your early diagnosis to a butterfly. So thank them. Hashtag superpowers. So what biomimicry is it? Just so we can get some definitional. It's not like putting in wood floors. That's bioutilization. We do that. We do it sustainably and unsustainably, hopefully sustainably. It's not bioassisted. This is an algae farm. It's not growing other organisms in order to, it's not using yeast to make bread. That's bioassisted technologies, again, going on for a long time. This is mimicking and valuing nature, not for what we can extract or domesticate or harvest, but what we can learn. It's a really different approach to the rest of the natural world. It's a different stance, the stance of student after a few hundred years of conqueror. It's a very, very different stance. We've spent a long time learning about nature. This is learning from nature. From a scientific standpoint, the questions are different. It's fascinating in that way. Learning from an organism, from an ecosystem, requires you to have a different stance, the listening stance, a noticing stance, but also to ask different questions. How are you doing this? In addition to why are you doing this, which is what we've asked as evolutionary biologists and biologists for years and years. We've asked why. Now we're asking how, and how might we mimic it? And there's nothing, there's a quote from the artificial photosynthesis folks at Arizona State University that I researched their work. And Devins Goose said to me, there's nothing that can make you tremble like going into a forest after you've spent your career trying to mimic a leaf. So now he's the trembling one. I'm interested in biomimicry as a sustainable technologies path and as a path to conservation, because it's a very, very different way of valuing the natural world. It requires us, I'm going to divide this up into some things that we all care about right now, some solution paths. It requires us to exercise a different way of seeing the natural world, not as a warehouse of goods, but as a mentor. So I'm going to give you a little practice. What do you see?
School of fish.
Yeah, school of fish. School of fish. Here's what John DeBeery saw. He's an engineer. He was at Caltech when he and his students had this insight. They studied fish, realized that the fish in a school are saving energy, especially in a forward-moving school like your trout if you're going to go fly fishing this week. The fish in the front, as they move in their sinuous movements, they throw off vortices. The ones in the back curve their bodies like a sail, and they're flung upstream. Takes a lot less energy just to surf, right? So you know what he did? This is the biomimicry part. He decided to make a wind farm out of that idea. So what happens with, and this is one of those, is turbulence a friend or a foe? Biomimicry teaches that it can be a friend. Horizontal axis wind turbines have to be spaced far, far, far apart because the turbulence, we believe, slows them down, the turbulence from one to the other. He took vertical axis wind turbines, put them in a fish school formation, and the ones in the front start to rotate, and they create, the ones behind them start turning even before the wind hits them. So imagine less land in cities, 5 times the wind power of the horizontal axis wind turbines. That's not a new technology. It's a new mental model. What do you see here? Humpback whale. Okay, look really closely. Okay, the scientist's name here is Frank E. Fish. I'm not kidding. I can't make that. Here he is. I know whales are a mammal. It's very confusing. He literally went into a souvenir store. He saw a statue, and he's a biomechanicist. He's a person who studies fluid dynamics and how organisms move through space, through fluids, air or water. He thought that the artist had made a mistake because there were these scalloped edges on the leading edge, and he's used to having things deal with drag on the follow edge. So he said to the person selling it, I think there's a mistake here. She said, I don't think so. So he got together with the artist, and sure enough, now Frank Fish has a company called Whale Power, and they're making fans for Enviro North fans, and they're testing wind turbines. What this does, when you put these on, it plays with the water in a way that reduces drag, 32% reduction in drag. The first time I told this story, there was a guy in the audience from Boeing. Do you know how much 32% fuel savings would be? At this point in the talk, he raced the stage with his card. And they had to pull him back. It was like a rock concert. They were like, not now, sir, not now. And he was just like, must know about that. I have to know. Anyway, it's called tubercle technology. So what do you see here? Yeah, the Holy Grail is what it is. The Holy Grail is artificial photosynthesis. It's not creating an electronic solar cell that works like a leaf. It's creating a device that takes sunlight, water, and carbon dioxide, which I think we have a lot of right now, and turns it into chemistry. That's what leaves do. Chemistry like fuel or carbon compounds. That's what leaves do. This is Daniel Nocera, who's doing it in something called the bionic leaf. He's cooperating with the bacteria at the end of the process. This is an interesting, the Joint Center for Artificial Photosynthesis, which should not get a Golden Fleece Award, but a Golden Goose Award for this, has been studying how to do this. And their latest breakthrough turns CO2 directly into ethanol and ethylene with only 2.5 volts of electricity. And that's solar electricity, all in one device. Imagine a device with water and ambient CO2 creating carbon compounds. Oh, that's a leaf. And it's everywhere when you walk outside. We're just now starting to get to this point. Here's a schematic of it. That's exciting work. Now, a leaf is a leaf is a leaf, not so quick. Look at this leaf. Many of them are wrinkled like this, but this is a particularly good one. This is John Buckham, and he's at both at Princeton and UPenn. This is simple. This is something that your 7th grader could notice and start to do experiments about. He said, why are some leaves so wrinkly? Does that help the light go in and begin to spend longer in its ability to get captured because it's bouncing around? And indeed, he found that that was the case. So he started to do thin film solar cell covers with this optical adhesive, very, very easy to wrinkle it. He could wrinkle it in all different ways. And he found that the wrinkling of the leaf was optimal for gathering 47% improvement in solar cell. And he looks like he's 13 years old. The people at Karlsruhe in Germany are studying black butterflies. The black is not made with a pigment, it's made with structure. And again, that black structure, there you can see it, it lets light come in, it drinks in light, and it keeps it from going out. And it's all to do with how small it is and how it relates to the wavelength of light, to its phase. So they're increasing light absorption by 200%. So in the renewable space, there's all kinds of people working on boosting our efforts. There's another one, leaf half antenna. There's a drizzle of photons that come down, and they have to catch, out of this drizzle of photons, they have to catch 2, not at the same time, slightly offset within picoseconds, in order to do photosynthesis. Statistically, it's like not likely to happen. They have antennae. So donor and acceptor molecules have been used now to try to do the same thing that a leaf does, which is gather 1 photon and move it along, gather 1 and move it along. That reduces losses below 10%. You will definitely see dragonflies if you go anywhere near the water here. And there's lots to see here. When wind turbines, horizontal ones, rotate very quickly, they can sometimes create a wall the faster they go, a wall to the new wind coming in. Hummingbirds don't do that. They're moving very, very quickly, but their wings are moving, they're morphing. The angle is constantly morphing. So scientists at Paris-Sorbonne studied what that morphing wind blade technology might mean for wind turbines. What if they were a bit movable? And they were able to get 35% more efficient at producing energy. So again, you're getting the idea here. That's again a yielding lesson. Electric yields 600 volts with life-friendly chemicals, created with life-friendly chemicals, not lithium, not any kind of rare earth, life-friendly chemicals. How do they do it? Finally, we're starting to be able to mimic what are called the electrocytes, these big stacks of cells that move sodium in and potassium out very, very quickly. So the folks here, and this is, again, most of these research projects are large. They've got lots of people involved. I'm putting the main ones here. They're using, those little dots are 3D printed. One is freshwater, one is saltwater. They have different ions. They literally take that and they put it into an origami that is also mimicking folding leaves and how they unfold. So there's a double biomimicry going on. This isn't ready for prime time yet, but I'm interested in this one, especially since it's really cheap and life-friendly chemicals for a new battery. That's how it works. This is a Galapagos shark. It's a basking shark. It doesn't move very quickly. And if you had a microscope and you were able to look at its skin, you would notice something amazing, which is that it has no bacteria on its surface. So Anthony Brennan said, oh, there must be an amazing chemical, a biocide, a new poison for bacteria. And what he found was, indeed it wasn't. It was a shape. On the left is the denticles on a shark. Bacteria do not, and this is very, very small, Bacteria do not like to land on that. This on the right is a mimic of it, and it's an Aurora, Colorado firm called Sharklet Technologies. Who's heard of Sharklet? They're doing thin films for hospital beds, for doorknobs, steel cases, making arms for chairs, for WeWork kind of chairs that are being used a lot. It repels bacteria rather than kill it. If you don't kill a bacteria, you don't reward those superbugs. So 271 people will die today of hospital-acquired infections in the US alone. That's a passenger plane. So this is a big one. A new way of dealing with bacteria that doesn't breed for resistance. Who's this? Did anybody know what this is? Any nerds? Tardigrade. Nerds? Yeah, yeah. It's a tardigrade. It's also called a water bear. Very small, little microscopic. It's probably in your water right now. Have a sip. They're everywhere. They're everywhere. And they can, when they run out of water, when they dry out, they do something, there's something called cryptobiosis, where they've got a sugar called trehalose that like shrink wraps their organs and their vitals. And it's like a glass, it's like an amber. It doesn't crystallize. If you and I dried out, we would crystallize, our sugars would crystallize and poke through our cell membranes. They don't. And they're able to, for decades, they're able to go into a done state. Okay, nerd, here's a real nerd question. Who played with sea monkeys when they were little? Oh yeah, that's why you're here at the Genius of Animals track. I see you. I did too. And anyway, you got them as dried little pellets, and then you added water, and poof, they started swimming around under your microscope, and that was pretty darn fun. This is Rolf and Judy Muller. They're in San Diego. They have a company called Biomatrica. They have mimicked the trehalose, the amber-like substance, and they're making biologicals, protein, blood samples, vaccines that need no refrigeration. So Project Drawdown says that the number one thing that we can do right now is manage refrigerants in order to reduce global warming. Because refrigerants are such a high potency greenhouse gas. All right, so manage refrigerants. What if we just don't have refrigeration needed? What if we can preserve without refrigerants? That's what they're working on. This is a hear question. What do you hear? That's how they talk to each other. That's how they echolocate. They send out a beam. What comes back? We thought they sent out a beam. Josephine found out that they send out, this is outrageous, they send out two beams, slightly offset in timing from one another, and of different frequencies along their path. So they're large and then they get small. And they intertwine in a beautiful little spiral. So that's what they're throwing out. And it's called pulse echo. Gave us a really, really good idea, because if we do that with our sonar, it helps us with ultrasound, again, back to health. But interestingly, now that we're looking at a big infrastructure move in this country, it allows you to see into bridges, to see under roadways without drilling to see what damage there is. That's a huge thing. It's a huge thing. I can't talk about food without talking about climate these days, because it's such, again, drawdown. Catherine Wilkinson is right here. No? Oh my gosh, you're a lookalike. A doppelganger. Anyway, Project Drawdown tells us that food waste, how we grow it, how we transport it, so important in climate. What do you see here? Kelp. Kelp, kelp, and a really cutie, too, really cutie, who lives in there, keystone species. This is interesting to me. This is a guy named Brent Smith, and he has studied, he got, Hurricane Sandy took him out of the oysterman business. He lost all of his oyster beds. So he decided to look at what he could do to farm seafood and have fish, create a habitat that fish would come into, rather than him driving all over the ocean trying to find the fish. And then he found out about kelp, and he found out that it's really, really good at sequestering carbon dioxide. So he started to talk to the chefs up and down the East Coast about, could we make food out of this kelp? And he also found out that the kelp really pulls in nitrogen plumes that are going into the ocean. And the problem with aquaculture is that you've got these nitrogen plumes. You know, if you put fish in a cage, you've got these plumes of pollution. This sucks up that pollution that's coming out of the Chesapeake Bay, for instance. So look at his thing. It's a 3D farming thing. So it's small area. You go with your boat and visit it every day. Fish come into that. And he's reversing climate change, global warming, while growing food, which is really, really interesting. So there's all kinds of new things in agriculture. I woke up one day, and this hippie magazine, Forbes, said this: move over genetic engineering. Biomimicry seems the better bet for solving global hunger. This was even news to me. I was just, wow, that's interesting. This is Rusty Rodriguez. He went, talk about noticing something, he went to the Yellowstone hot pools. And he saw something called panic grass growing next to the hot pools. And he said, this can't happen. I'm seeing something with my biologist eyes that cannot happen. A plant can't do this. It's too hot. And then he dug down and he started to look at the roots. And he found out there was a fungus associated with the plant that allowed it to grow in these hot conditions. And he began to find this everywhere. He now has a company. They inoculate seeds with a fungus that allows plants to grow in drought conditions. Rice grows with half the water. I honestly think that what we're going to be doing in agriculture over the next 20 years is not going to be so plant-based. We're going to be learning to help the helpers. We're going to be asking the plant and its microbes, what do you need? And how can we help host that? Materials. Is it a feedstock or is it a pollutant? Carbon dioxide, we think of it as a pollutant. The rest of the natural world, plants, all these organisms in the ocean, they're all made out of all the hard things in the ocean, the coral reefs, are all made out of dissolved CO2. Plants, CO2. It's an ingredient. So when you see that, do you see concrete? This is Brent Constance. He was a coral researcher. He read one stat which said that the making of carbon dioxide releases, for every ton of concrete made, you release a ton of carbon dioxide. And he said, that's crazy because I know corals do it the other way. They sequester, right? They sequester dissolved CO2 to make, with calcium, to make their calcium carbonate. Calcium ions, carbonate ions, dissolved CO2. This is a coral polyp. He has two companies, Blue Planet and Calera. They take CO2 out of smokestacks. This is happening right now at Moss Landing. It's co-located with a desalination plant, which produces brine, another environmental nightmare. You don't want to put concentrated salt into the ocean. So you take that salty water, very salty water, that comes out of desalination, and you've got all the minerals you need. You bubble CO2 out of it, through it. He doesn't use corals. He uses the recipe from the corals to create road aggregate, concrete, drywall. If you fly into San Francisco, the new wing spec'd his concrete, Blue Planet concrete. It sequesters CO2 so they can check that off. Why wouldn't we have all of our buildings doing that, right? Right? And all of our roadways. I mean, we have a lot to sop up. This guy's my favorite. Look at his face. This is Jeff Brinker. I wrote about him in my book. I love him. I love his hair. His hair stands up because he is so excited about everything he does. I am not kidding. Life does not manufacture using high heats. Heat, beat, treat, that's what we do, high heats, chemicals, high pressures. Life can't afford to do that because it manufactures in its own body. This guy has been figuring out how to do what life does. Shells self-assemble. Your bones self-assemble. You self-assemble. Spiders silk self-assembles, right? He's been doing this self-assembly thing, and he's very good at it. He's at Sandia and University of New Mexico. He's just come out with a new membrane. It has carbonic anhydrase, which is an enzyme that's in every one of your cells. It's what you use to sop up CO2. He captures 90% of CO2 emissions from power plants. 90%, that's unheard of. It's 70% better than conventional at $40 a ton. So if you're interested in the carbon markets and what's gonna go on, these kinds of technologies where you have carbon dioxide being pulled out of smokestacks and not released, let's not put it into the ground. Let's put it into our buildings, our plastics. There's people who do this. This is his device. It's amazing. Check it out. It's called a Memzyme. This is a company in California called Newlight. They make something called air carbon. They make a plastic out of CO2 and methane. And IKEA has just agreed to buy, their plan is to buy 1 billion pounds of it. They're gonna buy 50% of everything he's making right now. So look for your plastics, buying your packaging, buying your plastics that have CO2 sequestration, thanks to plant enzyme mimicry. This is a cool guy. Speaking of plastics, which we have a lot of right now, this is the waxworm. Beekeepers know about it because it goes in and it eats wax. It's a problem for beekeepers, like Frederica. She was a beekeeper, she's also a scientist. She picked up some of these waxworms off of her hives, put them in a plastic bag. By the time she got home, they were crawling all over her kitchen floor, because they ate their way out of the bag, right? So 90% of plastic waste is polyethylene or polypropylene. They eat it for breakfast. They love it. They love it. Now, are we gonna start farming worms? No, what we're doing is we're going and we're looking at the recipe. What is the chemical reaction that breaks down all that plastic that is in our oceans and in our landfills? I mean, this is while we stop creating the plastics to begin with that are not biodegradable, right? But what do we do with the legacy plastics? Thank you, waxworms. What do you see here? Peacocks, right? It's brown. That's brown. There's no color there. There's no color here. It's only brown, melanin, like your freckles. That's it. All of this, all of it. Melanin, keratin, which is like your skin or your hair, and it's also bird feathers, and air pockets. Light comes in and is reflected or refracted to create the color to your eye because of the way, the shape. Nature adds design to matter. Toxins, there's a lot of toxins in the fashion industry because of pigments. And in the paint industry, lots of toxins, lots of heavy metals. This would be an amazing thing. This is Ali, and I am not gonna try to pronounce that. Can anyone do that for me? Thank you. He's at University of Akron, again, like in the same lab with Catherine the Great. He studies, these are super balls he's making. Very, very easy manufacturing process. Those balls are very small. And when they pack together like oranges on a crate, he can control the air between them, so he can control the color. This is coming. Lexus has this new concept car that has structural blue finish. They're using metal flakes, but someday they're gonna use Ali's very, very non-toxic super balls, I hope. What do you see here? Mussels. Mussels. These mussels are undergoing incredible pressures, right? From all the water coming in and tugging on them. And they've got these beautiful things called byssus threads. And at the end of the byssus thread, there's a glue that glues underwater. Try putting a Band-Aid on and then going swimming. We're not good at gluing underwater, but they are very good at it. This is Professor Lee from Oregon State University. He literally just stood and looked at the ocean, went back in, started to read a bunch of papers from Herb Waite, and he said, you know, I think this is a protein that does this, and he understood the protein. He said, what if I substituted soy, which is also a protein, to make a glue? And he replaced all the urea formaldehyde glues that go into plywood. Now it's 60% of the plywood and veneer industry is using this muscle. So you probably, if you've made a home recently and you got a green plywood or case goods, kitchen cabinets, muscle inspired. And Megan is looking at the byssus thread, and she's making something that stretches way farther. So a plastic that stretches without breaking. Another thing we can do with plastics is just not have them be so brittle. Tuttle, Dr. Tuttle, thank you for that picture of the bat. But actually what I'm focusing on is there's an amazing relationship between that pitcher plant makes its echo chamber exactly for that bat's call, so that as it flies through the jungle, it can find the place it sleeps. It's a roosting bat. It roosts in there. And so, and then it poops, and the pitcher plant loves that. Gets all kinds of nutrients. So we also learn about mutualisms from the natural world. Anyway, pitcher plants notoriously have insects come in, but they can't go back out, and then they get dissolved, right? Here's another real hero in the field, Joanna Eisenberg. She's at Wyss Center for Biologically Inspired Engineering at Harvard. One patent after another. She's brilliant. She has something called SLIPS. It's slippery, liquid infused, porous material. What she found was the material on the inside of that pitcher plant, there's a fine film of water that's trapped in the material so that it can't evaporate. It literally is slippery to oil, water, ice. It's omniphobic, they call it, not hydrophobic, omniphobic. She has created in a very simple self-assembly technique, and now a company, a coating that is, imagine a coating for all the steel, all the infrastructure should have this. Corrosion resistant, ice resistant. Imagine flying without having to wait because ice doesn't form on the plane. Her coating, this SLIPS coating, seriously is a game changer. Self-cleaning windows, self-cleaning buildings. Boats that slip through without fouling. It's an anti-fouling, so bacteria and barnacles can't get caught on it. She's an amazing person, very quiet and humble too. She got together with Tak-Sing Wong, and he said, well, I know about rice. And rice leaves direct the water, they direct water away really well. So he took her SLIPS, which is very hydrophobic, and he put grooves in it like the rice leaf, and he's making sheets that gather fog for coastal communities, 120 liters of fog, of water per meter per day, which is a lot in a community, square meter of this material. Imagine getting agriculture started. It's just from the shape, just from the shape. Desalination. We're not the first to desalinate. This is Peter Agre. He found these pores that are in every cell in your body that move water through. Instead of reverse osmosis, where we push water against a membrane and then it gets clogged, your cells have these beautiful hourglass-shaped aquaporins that pull water through. They escort water through with nothing else. No pushing. Life is really elegant and subtle in its energy use. So there's a company called Aquaporin in Denmark that has made a membrane of this, very low energy desalination, highly, highly permeable, 100 times more permeable than reverse osmosis. Here's more kelp. For some reason, kelp keep coming up. Note the shape of the kelp. This is Jay Harmon. When he was 8 on the coast of Australia, he noticed that this long kelp were getting tossed about by the waves, and when he got tossed around, he had to hold on to the rocks. So he thought that the holdfast for the kelp must be very strong, but when he grabbed it, it wasn't. What actually was happening was the kelp was spiraling into a funnel that reduced friction, Fibonacci sequence it actually is, to let the water go through. Yielding. He's created what I just had there. How do I go backwards? That's a thing called a Lillian Peller. It has the same mathematics, and it goes into municipal water tanks, and it rotates the water with a very small amount of energy. It starts a vortex going in the water so that the chlorine doesn't get stratified, so you can use less chlorine in your municipal water supplies. And that's a San Rafael company. Kingfisher, this is Dr. Nakatsu. He's a birder. He noticed that kingfishers do not make a splash when they go into the water. He looked at the beak. He redesigned the bullet train, which was a bullet, and went into tunnels and made a sonic boom into a much more streamlined front. And you're driving a kingfisher beak. You'll also see those if you look carefully. This is Routific. You know, UPS and FedEx, they have these amazing, expensive algorithms to get their trucks to go in the most efficient routes. Bees and ants have that down. So these algorithms have now been used, and Routific is selling to small companies like florists. I could go on. But the question is, how do we make this not just a few scientists? That was the question 20 years ago that we asked ourselves. We said we need to bring biologists to the design table. That's what we need to do. And we need to train biologists to be able to see in this way. We've been working for 20 years. I have a consulting company called Biomimicry 3.8, and we've been working with companies like this. So companies like this that you may invest in are also investing in bringing biologists to the design table. You just don't hear about it much from them, but you will hear about it now that you've seen this talk. You'll hear about it in the media. It's in the zeitgeist right now. Here's what a few quotes. Number one innovation that could change the way you manufacture. And this is the Society of Manufacturing Engineers. Harvard called it one of the top 20 breakthrough ideas. Fortune said last year, 5 trends to ride in 2017. If you're not incorporating nature's most brilliant ideas into what you sell, you're leaving money on the table. That's really interesting to me, having watched this for 20 years. Patents are going up, papers are going up, institutions where you can study are proliferating, and you're using it every day. If you've got an iPhone 10, you've got a bio-inspired chip in there. That's why it's called a bionic chip. It's a learning chip based on how you learn, a neural network. So there's lots in the computing industry. You're using biomimicry. He knew this. He was hip to this. And he was working on it already. The question is, how do we get this out of just Jaguar Land Rover who can afford it, right? Or Apple who can afford it? We said to ourselves as consultants, we don't want to be the only ones doing this. We need a biological intelligence, not a GIS, a BIS. That's what we said to ourselves. So we created something called AskNature.org. Go on it yourself, it's really fun, but definitely tell your kids. And if you invent for a living, and I think we're all designers in one way or another, even designing teams or management teams, you type in a function and up comes the organisms that give you ideas. How does nature manage temperature, move silently, assemble, collaborate, communicate, form enduring partnerships? And up come the biological examples. It's the only place on the web that does this. We've only got 1,600. How many? Beth Ratner is the ED. Could you raise your hand? She's our ED. And what do we have? 1,600 strategies. That needs to be 16 million. We're working on it, but it's a really, really cool thing. You type in a strategy, you see how the natural world has already done it, and you're off and running with an idea that you can emulate. What we're hoping for with Ask Nature is to create the backside of Ask Nature. We're looking at indexing a lot more of the web and pulling it on. We've been working with, we had a detail with IBM Watson's team, and they looked at taking AI and putting it into this, because we're creating a Rosetta Stone between the ideas in engineering and the ideas in biology, or more like biology to engineering, right? A Rosetta Stone. It's not a trivial idea. It's not a trivial problem computationally. We're also trying to, in a Google-esque way, organize the world's information, biological information, by design and engineering function. Nobody's done that. But for us, we can't keep on boutiquing this. We need any inventor, anywhere in the world, at the moment of creation, to be able to ask, how would nature do this? And get an answer. Not only an answer, but what we're really, really hoping is that we can actually start to scan, and there's lots of organizations now that are starting to do this, scanning all those drawers that are in natural history museums, scanning organisms like that into 3D, so that that kingfisher, that guy who studied the kingfisher beak, that would be in Ask Nature. He would talk about drag reduction. He would download into his CAD/CAM program a kingfisher's beak model and start to play with it in silico, do wind tunnel tests on it. That's what we need. It's a huge project. Fireflies have this thing in their abdomen, it's just shape. And when you put that shape inside an LED bulb, it increases the brightness by 55%. That shape needs to be able to be a push button that you can 3D print your pattern onto the LED lights, right? Or dial any property that you want. That's when biomimicry starts to become in the tools designers use every day and engineers use every day. Because this is coming, where you push a button and you've got robots doing 3D printing of bridges and infrastructure, and you get light weighting that only the natural world can do. Or packing, when you pack concentrating mirrors the way a sunflower packs its seeds, you get a lot more, 22% more power. Because you have that much more space for the mirrors. This is possible now. It's just not tied into Ask Nature yet, where you can take a material or a structure and do what your bones do, which is your bones are constantly sensing, and it takes away material where it's not needed and puts it where it is needed. And there's a software program that has mimicked these bones, this bone reformation process. Imagine having that where you build your bridge and then you lightweight it with algorithms from the natural world. We need an Apollo project on Ask Nature. We really do. We also realize that how do we create more and more Jay Harmons and Joanna Eisenbergs? How does that happen? We have a global design challenge. And it's amazing. We get applicants from all over the world. Half of our applicants are girls and women, which is unusual for a science design challenge. Really, really unusual. We've had it now for how many years, Beth? 8 years, it's our 8th year. We say we're seeking a new species of entrepreneur. When we started, we would just have people hand in their designs, and they were fabulous, but they didn't really go anywhere. So now we have what's called a launch pad, where we're actually giving them business education. We're pairing them with mentors. And our last design challenge, out of the 7 teams, 6 of them are still going with their ideas. We've spawned 5 companies, 3 patents. We now have a $100,000 Ray of Hope Prize, thanks to the Ray C. Anderson Foundation. We had one on, I'll show you a few of these. What time is it? What kind of timing do I have? 5 minutes. 5 minutes. Yeah, 12:50, okay. 5 minutes, 5 minutes? A little. So here's some teams. I'll go very, very quickly through these. It's an amazing thing. Mainly these are students from Thailand. They entered our design contest to figure out how to capture insects. 2 billion people around the world get their protein from insects. But it's really hard to find them. So they looked again at pitcher plants, and look at this. It's in the Peabody Museum. Yeah, Thai weaving. You hang this outside of your home. Insects come into it, they can't go back out. They're from high school. So we started a youth challenge as well. This was our last winter. It gathers fog, it stores it, it distributes the water for urban farms. Really amazing. The mangrove still that didn't even win has just gotten 10 million euro from Dubai. So people are paying attention. This is a non-electricity refrigerator, and they've gone viral. They've gotten a lot of play. This is a company that's now in Boston. It's a coating company. They're at about 12.6 invested. So we're proud of them. This is the new ones. Look at these faces. They're from around the world. Look at them. They're full of heart. They're brilliant. Absolutely brilliant. They don't look like your normal white-coated. They look like a rock band. These guys from Georgia Tech. So beautiful, these kids. It's unbelievable. Kids, look. So, I don't know. That's what gives me hope. Nature is a source of wisdom, not as a source of goods. I'm hoping that that's what they're learning. And I know once you try this, I mean, then when they go into their professions, they're not going to make a design or a deliberation without asking, how would nature do this? I know that. I know that. So anyway, thank you so much for your kind attention. It was fun.
Hi, how are you? My name is Robert Cowan, and it was very interesting. It's new technology that is new to me. How much is the U.S. government funding this, and what country in the world is leading this technology? Are we or someone else?
It's a really good question. We are funding it to some extent through DOE, through Department of Energy. NASA's very interested in this work because they need to have, remote stations, and they need to know how to do things, right? Self-assembly from local raw materials is of great interest to them, and trying to have life-friendly things aboard spaceships and space shuttles. And we're working with them. They've got a big biomimicry program going on. National Science Foundation, there are many centers besides Harvard's. And so when I wrote the book 20 years ago, it didn't have a name. The field didn't have a name. And what I really hoped was that naming it would allow people to get research. I never thought any of this other stuff would happen. That has indeed happened. So yes, National Science Foundation has bio-inspired, biomimetic, there's different words for it, funding specifically for this. Yeah. As far as what the UK was early on with materials, Germany has a very slick research, a competence center of about over 50 centers that goes right into commercialization. They really support it, so there's lots of patents coming out of Germany, but China's right on the way. They've played catch up, and now I see so many papers and patents coming out of China. Yeah.
Thank you very much.
You're welcome.
Beyond high school, I have a son who's an engineering student, he's a freshman in his home in Indiana. And, thanks. He's also an Eagle Scout, and he did aqua farming for his Eagle project. So
cool.
He's very interested in the environment.
Yeah.
And he's so creative, he can always look at something, a piece of art, and just understand it on a different level from everybody else.
Yeah.
So would you sponsor gap years or some sort of way that I could introduce this whole idea to him? Because he's in engineering and he's in mechanical right now, but he doesn't really know what he wants to do. And I would love to see where I could, enlighten him, and I think it might be a great path for an actual engineer, because they don't offer this
Right.
at traditional engineering schools.
Yeah, I would really encourage him to sign up for the Global Design Challenge. You get trained in biomimicry deeply over a couple of years, and you get through us, through the Institute. And you also get, that would just be a good way for him to do it while doing his other formal education. If he wanted to go into this, there's a Center for Biomimicry that we are co-founders at Arizona State University. So there's an online course that he can take. There is a 2-year master's course. You get your Master's of Science in it as well. Arizona State University, the Biomimicry Center, yep.
Well, as a family therapist, can I find out how nature deals with anxiety and depression?
Yeah, the thing about, you got to be careful a little bit with the social innovation piece in the sense that we're not like bees. We're not like, we're a different species. We're a certain kind of species. So when we look to the natural world for ideas about how to network ourselves together, how to cooperate or communicate, we're looking across many, many species, not focusing in on one. It looks to see what emergent patterns come up, right? And I am sure that if you took that approach, not a species-specific approach, but a general sort of 360 look at how nature handles stress, I think it would be fascinating. I think you'd find behavioral things, and I think you'd find physiological tips.
I brought that up because I saw gibbons in central Sumatra, Indonesia, that when they got scared, they huddled together and they touched each other.
Yep.
And I wonder
Yep.
if other species have ways of dealing with that.
I don't know. I mean, there is definitely safety in numbers in many, many species. I mean, we try to look for design principles that are general. Because, gibbons are a particular kind of primate, we're a particular kind of primate. But it's definitely the Tennyson red in tooth and claw interpretation of nature in sort of this fundamental competition to the death kind of thing. It makes better television than it does science. What actually happens is that there's competition during mating within a species, but among species, different species, inter rather than intra, there's an awful lot of cooperation and mutualism, because it really does help you make the most of where you live if you're in partnership with another organism. So you might be interested in what's called mutualisms as a field.
Are any of these technologies being applied to assisting the ocean in healing itself? You said that kelp absorbs the CO2.
Yeah.
That the kelp absorbs the CO2, and anything that we can do to reduce the rising temperatures in the ocean through natural methods?
Well, I do like this. I do like this farming. If we're gonna eat protein from the ocean, I really do like this idea that as we farm, where the thing about the kelp is that it doesn't just sequester carbon dioxide. You can either eat the kelp or you can cut it and it can fall to the bottom and get sequestered. It also helps with the pH. Our oceans are acidifying. They're warming, yes, but they're also, as a result, they're acidifying. And I'm not a great fan of doing giant, sort of putting iron filings in the ocean. I don't think we know enough about the consequences of those large geoengineering techniques, right? To the extent that we can restore, protect, and emulate, that's what I always look at. To the extent that we can restore nature's healthy systems, life will try to heal itself. We have definitely, frayed this planet right now. You know, she's not endlessly resilient. But to the extent that we can do regeneration to get those systems working well, that's the protect the ones that are working well, restore the ones that aren't, emulate where you can. And that's what I think the 3D farming is doing, is emulating those kelp forests. Yeah.
Hi, Greg Hammer from Miami. I teach biophilic design from time to time, and I was just wondering, did you coin the term, or was that EO?
That was E.O. Wilson. That
It was
well,
E.O.?
Well, it was E.O. Wilson who, what biophilia is, philia means love. And he talked, E.O. Wilson, my hero, talked about humans' innate love of other organisms. And so now, then Stephen Kellert at Yale began to write an awful lot about biophilic design. So, and he unfortunately recently passed, but I would give him the, you know, he wrote with E.O. Wilson. So Stephen Kellert turned it into design. So that is trying to make our built worlds so that more nature is in our cities. It reminds us of being in the natural world where we evolved and where we naturally feel better.
But the term biophilia, was it?
E.O. Wilson,
It wasn't, okay.
biophilia.
Because I've heard people attribute it to you, but I wasn't sure.
Nope, nope, nope. Yep. Yep. Good. Okay, thank you guys.